Hey. So today we're going to be looking at the basics of matrix multiplication in linear algebra. So assume that we have these two matrices, matrix U and matrix V. Now, if I want to multiply them together, we would go ahead and write UV is equal to, and then we would look at the first row of U, and to make sure that this is even possible, the first row of U, and really all the rows of U, would have to have the same dimension, the same number of elements, as a column of V. Alright? So we go ahead and say A times G plus B times I. Alright? And then we look at our next column. And right next to it we do A times H plus B times J. Now if we go ahead and just do this for this here with both of them, and then this here with both columns, alright, this will give us the result. Alright. And from there, it will give us a matrix of dimension 3 rows, 2 columns. Alright, let's look at this in an actual example. So, in an actual example, say that we have matrix 1, 5, 2, 6, 3, and 7. Let me move that 6 down a bit. And then our V is 2, 9, 4, 2. There we go. So now, if we were to do this multiplication, this times this plus this times this for our first term. 1, 2 plus 5 times 4. And then next to it, we'd have 1 times 9 plus 5 times 2. I'm just going to go ahead and cut ahead and skip writing out all of this. So after doing our calculations, our matrix has come out to these summations, which if we go ahead and do them, gives us the matrix of 22, 19, 28, 30, 34, and 41. And that is our matrix UV. As we can see in our example, U was a matrix of 3 times 2, where 3 was our number of rows and 2 was our number of columns. And V was the matrix 2, 2. 2 rows, 2 columns. Now, why were we able to do this multiplication? Well, that was because our number of columns of our first matrix was equal to our number of rows in our second matrix. So if we wanted to generalize that, we would say if U is a matrix of dimension n times dimension m, and V is a matrix of dimension m times dimension p, then the matrix U times V is going to be of dimension n times dimension p. So our columns and rows have to match, and then the corresponding matrix has the dimension of row, column of our first matrix and the column of our second matrix, n times p. Alright, doesn't seem so bad. So if that's the case also, that means that n and p can be any numbers. The only ones that have to match are m and m. What if you're in a situation, though, where, say, V is a matrix of P times M, and U is still N times M. Well, we can just go ahead and take the transpose of V, which is going to then be a matrix of M times P. So instead, we can multiply U times V transpose to get our matrix of N times P. Alright, I hope that was helpful. Thanks for watching, and bye-bye!